Before we get into the really powerful combinatorics, we want to talk about events as they relate to set theory. We want to formalize mathematically the kinds of things we're talking about. Loosely speaking, an event is something that can happen. An outcome is a way that an event can happen. We're going to make the identification between events and sets, between outcomes and the elements of those sets. What that's going to give us is that the number of ways that an event can occur is going to be the cardinality of that set. An event whose form is E or F is going to correspond to the set E union F, and a set whose form is E and F is going to correspond to the set E cross F. The idea behind that is we need something from E to happen and something from F to happen, so that's going to give us the pair little e cross little f, which is a member of the Cartesian product. Here's the idea. In some lottery, you draw a ticket featuring a number between 1 and 10. You will win a $15 gift card if your number is 1, 2, or 3, and you'll win a toaster oven in the event that your number is prime. In this case, the event win gift card corresponds to the set of outcomes 1, 2, 3, and win toaster oven corresponds to the set 2, 3, 5, 7. We'll use G to talk about the first set. We'll use T to talk about the second set. How many ways are there to win any prize? All right, well, if you think about it, what we're really doing is we're calculating the cardinality of the set G union T, which we might remember from the first set of videos about cardinalities of sets, is the cardinality of G plus the cardinality of T minus the cardinality of G intersects T. All right, well, G has 3 elements, 1, 2, and 3. T has 4 elements, but that doesn't mean there's 5 ways that you can win because 2 and 3 are overlapping. So we have to subtract 2, and we get 5. There are 5 numbers in the lottery that will win you any prize at all. Suppose you buy 2 tickets. How many possibilities are there for the numbers on the 2 tickets? This question is asking us about any tickets at all. So what we're really doing is we're doing the sample space cross the sample space. The first omega being our first ticket, the second omega being our second ticket. And we know that that's going to be the number of tickets times the number of tickets. So 10 times 10 is 100. Another question we can ask is how many ways could you win on both tickets? Well, we know that there's 5 ways to win. Maybe we'll call W the set 1, 2, 3, 5, 7 of potential winning numbers. And the cardinality of winning on the first ticket and winning on the second ticket is winning times winning is 5 times 5, or 25. We have to assume there that there's an infinite number of toaster ovens, but let's go ahead and do that. This question is a little more complicated. How many ways do you win on either ticket? Right? That includes winning on the first ticket, winning on the second ticket, or winning on both tickets. If you win on the first ticket, there are 5 options for your first number times 10 options for your second number. Plus, winning on the second ticket, you have 10 times 5 ways to do that. But notice that both of these situations include winning on both tickets. So we need to subtract that overlap. So 50 plus 50 makes 100, minus 25 is 75 ways to win on either ticket. There is another way to handle this problem. We know that the sample space of all 2-ticket configurations is 100. And since there are the same number of ways to lose on both tickets, because it's 5 of one and 5 of the other, as there are to win on both tickets, then that means there are 25 ways to lose on both tickets. Therefore, 100 minus 25 gives you 75 ways to win on a ticket. Sometimes we can count things indirectly by counting the complement.